Everything okay up there? Rock and roll. Okay, we'll start right now. Good evening. Welcome to the Ottawa Centre May meeting, May 2015 for the record. I'm Chuck O'Dale. Mike is away for this meeting, so I'm going to be your guide for this evening. And first of all, is there any first-time attendees here tonight? Except for Paula, our speaker. Well, welcome. Okay, let's see if Mr. Computer works. Whoa, there we go. Okay, tonight, that's me. I'm just doing the introduction. We'll have Dave give the sky, what's going to happen up in the clear sky tonight, by the way. And Paul Sokoloff has a very interesting talk about potential Mars. With a break, and Al will give us our latest advances in modern cosmology. I love it. And lots of observations tonight, and a few announcements. So, without further ado, let's rock and roll. Amanda McLaren, brand new member. Is she here tonight? Welcome. You're in for a great ride. We love it here. And we have lots of new members this year. We love young new blood. I'm just being old fart, so I have to pat. Oops, sorry, I can't say that, eh? Welcome. So, members in the news. What do we got here? We have, I can't see the name. Here we are. Shane Finnegan. Shane, are you here tonight? Ah, Shane. Awesome. Yeah, Shane gave us a picture of the. Why don't you explain it?
This winter I was, I guess, getting a little tired of hearing people complaining about the cold. So I was trying to find some motivation. On that day it was about minus 25, not including wind chill. And I was out walking the dog and I noticed this, so I ran back, got my camera, and grabbed this one. What's unique about this one is you're kind of getting three things here. You're getting the sundogs, the light pillar, or the solar pillar, but you're also getting the arcing.
Yeah.
What date was that?
I'm trying to remember. I think it was around January 20th. There was several days in a row where I was going out.
January 20th.
Oh, it was, yeah. But like I said, so there were several days there where I was able to get sundogs, but not like this one. This one was truly unique. Like I said, because you were getting the three different phenomena there.
Oh, thanks very much, Shane. That's a great image. Oh, what's this all about? Oh, yeah.
Let me help you with your memory. Keep going. Just press.
Well,
You recognize this?
apparently a couple of guys went up to northern Quebec and went around a crater. Oh, wait a minute, that was me.
That was you. Tell us
Well,
about
I'll
it.
give you the floor then.
No, tell us about it.
Okay, well, Eric, he's the guy that's normally behind the camera tonight, Eric Kajala. We had the excellent opportunity to fly up to northern Quebec to the Pingula crater, the old Chubb crater, aka New Quebec crater. And we had an interesting walk around that hole in the ground. It was one of the most pristine craters on this planet. And if anybody ever has the opportunity to get up there and look at it, it's totally awesome. And I have a good report of it, our trip on the website. Please, if you have any questions, tell me or go on the website and have a look. It was a great time. And you're going to say something, Ryan?
Yes, go on, please. Next slide. Second in the news tonight. It has been brought to our attention that this is Chuck's birthday today.
That's
Congratulations for completing another good job.
Happy birthday to you.
Many more.
Oh, Sylvie. Yeah, Sylvie said she's going to heckle me tonight, so you did.
No, my job's done. I can go sit down.
There we go. So one orbit around the sun. That was cool. So they say birthdays are good for you. The more you get, the longer you live. Yeah. So I'm collecting as many as I can. Okay, where are we here? There we go. Dave, you're up next with the sky this month. Hopefully we're going to have lots of good sky.
Yes, hopefully.
Here's your laser for you.
Great, thank
I
you.
can advance if you want.
Okay, yeah, that would be good. Well, good evening. Maybe the next slide. Okay, hopefully I can do justice to this. This is my first time doing this. This is the moon phases for the month of May. You can see we're almost at a full moon. Full moon is on May the 3rd, and the next full moon is July 1st. Okay, next one. Okay, May 5th and 6th, we have the Aquarids meteor shower, and it will appear to come out of the constellation Aquarius, and we'll see about 30 sightings per hour, but unfortunately there's almost a full moon, and so it will not be as clear as it could be. So it'll be washed out somewhat. Next one. Mercury. On May 7th, it will have the greatest eastern elongation of Mercury, 21.2 degrees from the sun. So we can look for it low in the western sky just after sunset. If we go to the next slide, you can see there's where Mercury will be. And that's that one was taken about 9:15 in the evening. That's a snapshot from Stellarium. Next one. Venus will be setting near midnight all month, so you should be able to get some good views of that. Mars, basically not visible. It sets around 9 o'clock. Jupiter. Okay, so we've got good visibility, setting at 2:45 a.m. and then towards the end of the month around 1 a.m. On May the 27th, starting at 10:01 p.m., there's going to be a double shadow transit of two of the moons, Io followed by Ganymede, and it's at a decent time as well, so maybe we'll get some pictures for the next month's meeting on that one. Saturn. Saturn will be visible all month. It rises at 9:51 today, and by the end of the month, we'll be rising at 7:42, so we should be able to see that during some decent hours. On May the 23rd, it's at opposition, basically a closest approach, opposite the sun. And reading up on it, the way it's tilted right now, we should be able to get a good view of the rings. Uranus is not available, or not available, it is available, but it's just not visible during May. And Neptune rises about 1:45 a.m. in late May. International Space Station. I happened to see it about a week and a half ago. I was out picking up my son from youth group and just looked up in the sky, and there it was. Unfortunately, all the best viewing times for the International Space Station, by best viewing I mean directly overhead and for the longest time, are middle of the night. So if you want to get up early on May the 17th at 4:43 in the morning, you'll be able to get a good view of the International Space Station. The yellow line here indicates the approximate path, starting here and going across there. For those of you who are maybe newer to astronomy, this is taken straight off of the Heavens Above website. It's a great website for getting information like this. And I think that's about it. Oh, one more thing. I thought I'd leave you with that little cartoon. Thank you.
Thank you very much.
Yeah, perfect. One night I saw the ISS go by Orion, and Orion had 4 stars, and I missed the shot. It would have been perfect. Yeah. Okay, where are we here? Okay, we are very fortunate to have Paul Sokoloff. He is, well, I'll give you the intro here. Botanist at the Canadian Museum of Nature. He specializes in biodiversity of plants in the Canadian Arctic. Paul's interest is in photosynthetic organisms in extreme environments. Paul applied this science during his Mars Arctic mission. This is what he's going to talk about. So would you please welcome our future Martian, Paul Sokoloff. It's all yours, Paul.
Perfect, thank you.
All right.
Thank you, everyone, for attending tonight. Thank you, Chuck, and happy birthday. Right off of the bat, no, I'm not an astronaut, but thanks to a TV crew that visited me while I was at the Mars Desert Research Station, I will play one on TV. As Chuck was mentioning, I recently had the opportunity to participate in a mission to the Mars Desert Research Station, which is just outside of Hanksville, Utah, with the hope of continuing on to do this kind of research in the Canadian Arctic at the Flashline Mars Arctic Research Station that's placed at Houghton Crater on Devon Island. And also before anybody asks, I'll get this right out of the way. Yes, I've read The Martian. It's the book where a botanist got stranded on Mars. If I ever go, I'll make sure that I'm on the return vehicle. Thank you for your concern. About a year ago, maybe I'll back up. So when Paul was about yay big, Paul wanted to do two things for a living. Paul wanted to camp all the time for a living, and Paul wanted to go into space. Well, I ended up going the camping route. I work at the Canadian Museum of Nature as a botanist specializing in Arctic plants. This means I have the great privilege of joining many Canadian Museum of Nature expeditions up to collect plants in Nunavut, Northwest Territories. But I've never really given up on little Paul's dreams of traveling into space. And so about a year ago, when I saw the Mars Society, that's their logo right there, advertise for candidates to take part in a simulated Mars mission in the Canadian Arctic for a full year, I thought, okay, why not? No, it really didn't take much time at all before I was convinced that this is something that I wanted to do. If you're not familiar with the Mars Society, they were founded by Dr. Robert Zubrin in the 1990s as a space advocacy group. Essentially, their mission is to get people to Mars. And the way they do this is by advancing research into human expeditions and colonization of Mars by operating 2 research stations where we can conduct simulated Martian fieldwork. So I applied to the Mars Arctic 365 program. That's the year-long simulated mission to Mars on Devon Island. As a shock to me, because I'm a botanist and there are no plants on Mars, I was selected as one of the finalists. And so, along with 20 other people, I was asked to go to the Mars Desert Research Station in southern Utah to test, to see how we would do during a small 2-week simulation as a precursor to selecting the final group for the year-long mission to Mars. And so this is the mission patch for the Mars Arctic mission here on the left. And on the right was our really quickly designed mission patch for our group, because we realized once we got to the station that, we didn't have a cool mission patch like everyone else. I will say, though, that we at least spelled Arctic correct on our mission patch, and I'll say no more about that. Sorry, I had to say that. So this is the Flashline Mars Arctic Research Station, or FMARS for short. That's on just on the edges of Houghton Crater, which is an impact crater. I don't have to tell you guys that. Normally I'm talking to biologists and they're like, oh, meteorites, cool. This is situated on the edges of a Houghton Crater on Devon Island, which makes it an ideal site not only to study impact formations and how meteorite impacts affect life in the craters, such as endolithic bacteria and rocks. But it also, because of the desert-like conditions, make it ideal for simulated Mars missions. Essentially, any technology or crew dynamic experiments that we can devise here will have some sort of fidelity. That means that, we can test rovers in desert environments. They're cold, they're dry. It's as close to Mars as we can get without sucking out all of the air, replacing it with unbreathable carbon dioxide and other gases, and lessening the gravity. Really that wouldn't be that fun, although it'd be cool if we could do it. With the idea that I could be spending a year at Devon Island in my mind, I arrived here. And this is the Mars Desert Research Station just outside of Hanksville. It's designed to approximate what life would be like on Mars for early expeditioners as closely as possible. So you see that you've got this squat little cylinder. This is the habitat, or the HAB for short. It's round because it's designed to fit in under the cowling of a rocket. Really The idea being that this is the first people on Mars, and you've brought everything you need with you. We also have the green hab, which is the little cylinder right to the right of it. This is the greenhouse for growing fruits and vegetables and recycling your oxygen and gray water. And a little further to the right, you see is kind of an imaginary tunnel leading away to the observatory, which is where you can actually get a lot of fantastic images because the night skies are so spectacular in this remote part of the States. So here's the hab again. It's a lot bigger on the inside than it looks like on the outside, which is good news because even 2 weeks cooped up with 6 of your closest friends can start to feel a little unnerving, especially if you're used to getting outside all the time. Once you start the simulation, once you're in sim, you're stuck there. And essentially, you live in the habitat, and when you do leave, it's only on approved EVAs by mission control, and only for short periods of time, because in an actual Martian environment, EVA crews would be subject to higher radiation than they would be on Earth. You want to control that, so you end up spending a lot of time inside. And so you'll see the effects of that on our crew very shortly. Again, the idea about situating these research stations in the deserts is really because they approximate what life is like on Mars. And just looking at this photo overlooking the San Rafael swell, that's the desert that MDRS is located in, if you can suspend disbelief and maybe not pretend the sky is a little less blue, it certainly looks like you could be on Mars. Just ignore the plants. So I mentioned that I was one of 21 finalists for a spot on the Mars Arctic 365 mission. We were the second crew of finalists to arrive, crew 143. That's us there on the right, the 6 people on the right. We had replaced crew 142 on the left, who had spent most of their mission, I understand, plumbing the toilets and catching rats. Apparently the rocket had stowaways. Needless to say, we were very happy that they had opened the hab for us and that we could get right into our simulated mission. And so, they look a little tired and we're all fresh-faced and ready to begin 2 weeks on Mars. We had an international crew. We had 3 Canadians, 1 American with the largest flag. He was great, though. We had 1 Russian crew member with our poorly drawn Russian flag in pen, in Sharpie, and 1 person from France. And so, a lot of red, white, and blue. But certainly, for all intents and purposes, with 3 Canadians on the team, we were Team Canada, and we let the world know this. It was kind of neat, too. French was actually the official language of the HAB, so I got to practice that at least. So to introduce the rest of the crew, we have going from left to right, Claude-Michel Laroche. He's from Montreal at the far left. He actually works at Measurement Canada. He's an inspector there for a living, part of the Canadian Forces, and at the time was one of our 2 Mars One hopefuls on our team. So here is a man who was willing to go to Mars for the rest of his life. Unfortunately, since then, he's actually been cut from the process. To his right is Paul Knightley, who is our American crew commander. He's a geologist by training, absolute nut about space and about storm chasing. So he was a hoot to have around. We had to rein him in whenever there was a thunderstorm. No, don't break sim. To his right is Anastasia Stepanova. She was our Russian crew member. She was the other Mars One candidate who's actually made it to the top 100 of that process. And I kid you not, she has a degree in space journalism, which is a really cool major. Why couldn't I have known that was a thing? She actually learned journalism from a former cosmonaut from the USSR, now Russia. So pretty interesting stories, mostly involving vodka on the International Space Station. We all know it's up there. To her right is Ian Silversides, who is our other Canadian. He's also from Montreal. And Ian is actually interested in doing his PhD. Right now he works as an aerospace engineer at Bombardier. he's interested in doing his PhD in spacesuit design, so I think he'd be a very interesting candidate to have with us up in the Arctic, mostly because he could probably make improvements to the suits, because they're kind of clunky to wear right now. And finally, on the very far right is Alexandre Mangeot. He's from Bordeaux originally, but now is actually doing a postdoc with ESA, the European Space Agency. And I just think it's really cool that finally I get to say I have a rocket scientist friend. He worked on advanced propulsion concepts for his doctorate. He was also the only other person who had been to MDRS before the rest of us showed up. So he was a wealth of insight into how the hab worked and how parts of it didn't work so well. I should also mention that none of us had ever met each other before we showed up at the station. So it was very interesting to get to know 5 other people in this context. Kind of, okay, am I going to be able to live with this person for a year? Fortunately, we were all tight friends by the end of the program. By the end of 2 weeks, we were joking, we were laughing, we were making really inappropriate games of Cards Against Humanity happen. It was a lot of fun, and so we really enjoyed our stay. But it's not all fun and games. We were there to do a 2-week trial, and so that's what we probably got down to doing. After spending one last night outside in freedom and walking around without simulated spacesuits on, we quickly entered HAB, and so and that's the full simulated Mars mission. So we got to know our living quarters for the next 2 weeks, and I'll give you guys a brief tour here. The habitat itself is 8 meters in diameter, not a lot of space. In fact, the habitat itself could probably fit easily in this room with room to spare. You enter through the main airlock, and I'll just show you here. You've got your EVA prep room where you hang up all your suits, biology and geology laboratory, and it's actually fantastic that it's so well equipped. We didn't have to bring any equipment with us. It was all there waiting to go for us. A workshop for the engineers, and the engineers love to tinker. A sink and shower. The thing about the shower is we didn't use it. The actual Martian mission would be under severe water rationing, and we decided to take that to the logical extreme and not shower for 2 weeks. Baby wipes are your friend. Once you go up the stairs up to the upper level, you enter the communal area, and so that's the dining area, the crew bunks, and where essentially all of the work takes place, and countless hours filling out reports for mission control. So this is the main airlock. When you enter it, you are immediately greeted by the Martian tricolor, and if anybody's ever read Kim Stanley Robinson's excellent Mars trilogy, you'll recognize the color scheme immediately. It's red, green, and blue, representing red Mars, green Mars, and blue Mars, or potentially where we could take Mars if we ever decided to change it and terraform it. Once you're through the airlock, you enter the lab, and you might get the impression that it's not super big, and that's completely true. But as a botanist, I only need enough room to press my plants, and I'll talk a little bit about that later. So it was more than adequate for my needs. Once we move upstairs, you see that this is the largest room in the habitat here, the kitchen/work area. So Paul is making us dinner, as he often did. He also introduced most of us to Velveeta cheese, which I guess is an American thing. It's pretty good, but I wouldn't want to live on it for 2 years. And of course, a lot of computer work. Every night we would spend approximately an hour reporting back into mission control during a comms window that simulated optimal communication times between Earth and Mars. This was my room, and there was no prize for guessing my favorite color. It's just like Mars. You can tell they're not super big. You're packed in a little bit like sardines, but at least the rooms are private. And they really, they give you the impression that if we do go to Mars, the first people going there will have even less privacy, so you're pretty grateful for having at least a closed bunk. And a place to unwind, because really there's nowhere else in the hab you can't go where there are other people. So, it's nice to have a little refuge. The greenhouse, and this is where we theoretically would have a healthy crop of tomato plants growing, but apparently the tomato seeds were no good. So all we had was wheatgrass. There were a lot of smoothies made on Mars. Here you can see Claude Michel Laroche taking notes. For some reason, they put the physicist in charge of the greenhouse and not the botanist. May have something to do with the fact that I kill plants for a living. He did a great job. So. And of course the observatory. And unfortunately, this would have been good to look up. I don't know what kind of telescope is in it, but I can assure you it's a good one. Just ignore the plants along the bottom. And of course, after being inhabited by 142 successive crews of potential future Martians, there's a lot of humor on the walls in the Hab. Is There Life on Mars actually became kind of the theme song of our crew. But really, Martian octopus likes to fight. I mean, come on. That's funny. So we settled in fairly well. Our food consisted mostly of shelf-stable and freeze-dried ingredients, just like any future crew to Mars would have. It was well-stocked with the most important supply that a Martian mission will need, coffee. Yes, we're all caffeine addicts on Mars. And as you can see, our crew is fairly young, and the common theme or the joke that we came up with was that we're the millennial crew. We were the new generation crew. Woo. And you'll see what that's like later. So once we had inventoried our food, entered the sim proper, we began experiments. They included continuing some of the experiments started by Crew 142, like this experiment where they were trying to grow radishes in simulated Martian regolith. I don't know if you guys know this, but when Viking landed on Mars, the first Viking lander landed on Mars, it sent back a chemical composition of the Martian soil that has been used to create simulated Martian regolith ever since. And this is actually commercially available in the States. So anybody who wants to can try growing plants in Martian soil. This group took their experiments to the next logical step. One of Mars soil's major deficiencies is nitrogen, so they applied simulated urine to the Martian soil to see if radishes would grow better. They did. We also were in charge of setting up the hydroponics system in the greenhouse here, and so Claude Michel had a real fun time trying to figure out how to get the water cistern from overflowing again and again and again. I mentioned that engineers like to tinker, so here we've got our two engineers, Alexandra and Ian, essentially creating new sensors in the lab. Alexandra brought blood pressure cuffs to look at physiological differences between work inside the Hab and work in spacesuits outside of the Hab. And of course they didn't work. So whereas a botanist might say, oh, well, there's the experiment, Ian actually made entirely new sensors in the Hab from scratch, which I think was impressive. And he quickly earned the nickname MacGyver, to which he asked, who's MacGyver? We filled him in. And Ian actually wanted to run an experiment using an in situ resource utilization experiment, which is essentially using what you would have on Mars. He found a ready supply of gypsum near the Hab, and so he actually ground it up and made casts, and we had a lot of fun setting each other's pretend broken bones. But that's a kind of ingenuity that would serve future Martian expeditions well. Other experiments included testing soil density or measuring soil density of simulated Martian soils around the Hab, which was really more of an experiment of how many dirty dishes can we make down in the lab, as you can see here. But actually, I think Alexandra got some really interesting data that will be used to help modify soil probes further on down the line. Life inside means that you have to get a little creative in terms of exercise. I led a few yoga classes while we were in the Hab. As you can see here, we've got some really great aspiring space yogis. Interestingly, Crew 144 actually brought a biofeedback monitor to test whether or not yoga increased mindfulness during their crew's mission, and I think that'll be really interesting to see once the results are available. Food was very important to the Hab. Well-fed scientists are happy scientists, after all. Caffeinated scientists, too. And Ian quickly surprised us by being an amazing baker. And so we ended up baking a lot of food. And true to our millennial reputation, I think there's a Mars Food Instagram account now. It's really cheesy. And we were also at the Hab over American Thanksgiving. And so what else could we do but have a traditional American Thanksgiving meal, complete with a weird Spam turkey? That's it there. It looks nothing like a turkey. It's very mash, isn't it? But it's amazing what little ingenuity can do. And actually, one of the founding goals of MDRS was to actually research food that astronauts could bring with them to Mars. Food studies are very important at Mars Desert Research Station, and there's a whole program of food science research into how can you make shelf-stable, appealing meals that will sustain astronauts over the long term. We were ridiculously proud of our food, ridiculously proud. One of my alternative roles at the Mars Desert Research Station was the health and safety officer. Because I am used to remote fieldwork, I have advanced first aid certification, so I was there to teach everyone else what to do in an emergency. With actual medical emergencies, this is one of the few situations where you would break sim, but it was often helpful to do simulated medical emergencies on Mars because, well, if an astronaut on Mars actually breaks their foot out on EVA, you can't just call for help. You actually have to deal with it there. And so medical science is also one of the core research aims of MDRS. Don't worry, Ian's fine. And yes, I know that you can't use your thumb to take a pulse. Of course, everyone thought it would be really helpful if I taught them how to preserve amputated limbs. Because if you've seen Total Recall, you know that amputated limbs are a very real hazard on Mars. I tried to find the video, but it wouldn't work. And I mentioned before that the night skies there were absolutely fantastic. And so every free minute we had, we would actually sneak out into the tunnel linking the observatory and the habitat and partake in a little astrophotography just because the night skies were so vivid. That tunnel is interesting because it's not supposed to be there. To reinforce the sim, you would want the tunnel to be closed off. And really, you're just kind of pretending that the tunnel is there, using the power of imagination. But apparently this has been controversial because some teams have imagined tunnels going all the way to Hanksville and the pizza station there. So we stuck with just the one pretend tunnel that made sense, but we did use it. Believe it or not, we're doing science here. Alexandra is seeing how quickly we can learn to do two-step line dancing. I'm terrible at it. Look, I'm trying not to fall over. But the idea being that if you're on Mars and you need to learn something in emergency, how quickly could you do it? The answer, not that quickly. At least for dancing. I mentioned we were the Millennial Crew, and one of the core research aims of the Mars Desert Research Station is outreach. Essentially, if the political will to get us to Mars doesn't exist, then we won't get there. Quite frankly, we need governments who are invested in manned expeditions. So outreach is important. And so I tried to do my best to talk about why it would be important to learn all we can about Mars while still on Earth. So this included blogs for my home institution, the Museum of Nature, who's never had any sort of Mars affiliation before, so it was really neat to take us in a new direction. Twitter is, of course, a great outreach tool, and this is where I say we're the Millennial Crew, because I don't think I've seen a group of more excited 20-year-olds as when the Canadian Space Agency retweets you. That was a lot of fun. And as well, Outpost Magazine, which is an adventure travel magazine, will be running a 4,000-word feature on our rotation at MDRS coming actually this month. So once again, outreach, like what I'm doing right now, is really important to the cause of future manned missions to Mars. But of course, nobody is going to go to Mars just to stay inside a habitat the whole time. We eventually had to go outside, and we were really chomping at the bit to do it. And so we would get into our simulated Mars suits. You can see on the left, you strike a really dapper orange figure in that. Getting into them, on the other hand, as you see with Anastasia on the right, is a different matter altogether. They're just about as frustrating as a real spacesuit would be to put on. You have to put on coveralls, gaiters, boots, gloves, backpack, helmet, all in that order. And it takes about an hour to get into it if you're not experienced, which is true for astronauts on the ISS. Of course, it's always helpful when you have friends to help you out, and so Claude Michel, Team Canada, once again, getting a hand putting a spacesuit on. Due to safety regulations as well, 2 people always have to stay back at Mars Desert Research Station. I always thought this was because if something happened to an EVA crew, at least there would be a backup crew. But it actually turns out that about 5 years ago, somebody pinpointed MDRS on Google Maps, and now people are always coming up to see what the Martians are up to. So you want to be there just in case somebody starts rifling through the HAB. Once we would get all together and once our suits were on, then we could actually finally proceed outside with our EVAs. So we would all gather into the tiny airlock and wait out a 5-minute simulated cycle of decompression going out and recompression coming back in. The first time we did this, we were all very serious. We were talking about, okay, this is the plan for the EVA. We're going to go here. We're going to get these samples. We're going to do that. By like EVA 5, we were piping in ridiculous music over the intercom. And I think by the last EVA, we were just too tired to bother. So we had a grueling schedule, 1 EVA a day, every day. And so we actually got a lot of our research goals accomplished as a result. And so you can see here on the right, we're heading out of the airlock and onto the Martian surface for the very first time, which looks nothing like Mars, incidentally. So I'm a botanist, and I make no bones about that. I'm most interested in plants and the kind of life that can live in these extreme environments. And so a lot of our EVAs took us to environments like this, where plants had actually overtaken the desert and were in the process of primary succession, so kind of going back to the land and starting up an ecosystem. And what I was most interested in doing was actually developing a flora, or a complete list of all the plant species for MDRS. While a lot of astrobiological research has happened at the station, nobody's ever gone and created a species checklist because it hasn't necessarily been relevant. You're normally only looking at 1 or 2 study species for certain experimental variables. But with a complete species checklist, which is fortunately for me something I do during my day job, we can actually essentially provide the Mars Society with a resource that future crews can use to validate the results. Here are what experts think are present at the station, and here's what you can use as a reference for identifying biological specimens. So we would head out on ATVs, or as the Mars Society calls them, light unpressurized rovers. Once again, that's SIM, permeating all aspects of life. And when they worked, they were actually the funnest way to get around. It beat hoofing it on foot a lot. And it was a great way to see the desert too. And you know, Ian was having a lot of fun with it too. We were a goofball crew. Another research project that we undertook was under Paul Knightley's supervision. He's the geologist and the commander. He actually designed and developed a soil vapor probe for detecting subsurface soil vapor in the desert, with the idea being that future astronautical crews to Mars would want to look for subsurface soil vapor in the search for life. As part of that experiment, he was also training other would-be geologists in its use, and here you can see Anastasia perfecting her soil coring technique. Of course, a lot of our efforts were eventually documented by film, and I said I'll be being an astronaut on TV. And that's because as part of the outreach aim of MDRS, sorry, that's really badly positioned for me, I talk with my hands, is outreach. And so we took the opportunity to invite a French TV station, Arte, to come film us while we were out doing our EVA sampling. And then brought them back to the HAB to talk about why MDRS exists. It was interesting working with them. They would fly a drone overhead and to film us, but then, you know, after about half an hour of that, they would make us all go back to our positions because one person had not been doing something they wanted us to do. So, you know, science in the service of media. But fortunately, when the TV crews weren't around, we actually got down to our proper sampling. Interestingly, we also had another media crew come by. This was from the tabloid, I guess is a nice way of putting it, Paris Match, which is a popular magazine. They sat down with us and we got to talking, and they asked us, they said, so how much faster than the speed of light does the space shuttle travel? Which is when we knew we were in trouble. So, you know, we politely corrected them and said, well, it doesn't actually travel faster than the speed of light. We can't do that. And they said, oh, okay. So then they asked us about the gravity and how we would simulate low gravity on on Earth. And we said, we can't do that. And they said, well, can't you just suck the air out of the room, thinking that air pressure is what's holding us down to the ground? But my favorite part was when one of them picked up a piece of paper, and we all knew what he was doing, but we said, no, he's not going to do it. No, he's not going to do it. He had just gone to see, I think he was just talking about Event Horizon. He starts folding the paper up. He says, can't we just fold space? And that's about the time that we all lost it. So as you can see, we've got a lot of outreach left to do. Another task that we were assigned while we were at MDRS was to complete the tunnel between the observatory and the HAB, thus making it a little less in your imagination when you're walking between the two. So here we are performing a little bit of space construction. Anastasia, who is here on the left, was actually looking for meteorites with her stick. She had attached a rare earth magnet to her to the end of this pole and was looking for nickel iron meteorites in the desert. Unfortunately, she never found any. But they were really, really helpful field botanists, and they helped me with my collection effort immensely, and so I can't thank them enough. So here we are, collecting plants, which is essentially just digging them up, bringing them back to the lab to press them and dry them. And then once they're back here in Ottawa, we're actually working on identifying them and storing them as a reference collection at the Museum of Nature. So there are all sorts of different Martian plants. We've got the desert trumpet on the left, this sort of weird alien-looking thing in its own right. And on the right, we've got the big stem rabbit bush, Ericameria nauseosa, named over the fact that it will make you nauseous if you eat it. Don't eat it. Opuntia basilaris, prickly paracactus. And you'd think you wouldn't have to tell a botanist not to pick this up. You'd be wrong. I spent about half an hour picking spines out of my gloves after I got back, and they're the really tiny ones that went right through the gloves too. All for science. And lots of species of astragalus, which are called locoweeds. This is actually interesting because it's the most diverse genus of plants in North America, and this area, the San Rafael Swell, was the most diverse area for astragalus. So we're actually right in the center of diversity for this little unassuming bean-like plant here, which is ridiculously pretty, and you know, I bet you guys don't see a lot of flower pictures at these talks. The salt cedars, Tamarix chinensis. Appropriately, this is an invasive species in southern Utah, so here we have an alien meeting another alien. I know. And plants like Artemisia filifolia or narrow-leaf sagebrush. And so, once again, the more we can learn about the photosynthetic life at this station, the more we can apply that to future astrobiological work here. Lichens, of course, making up one of the most interesting floras in the desert. They're radiation resistant, they're drought tolerant, and they don't need a lot of oxygen to survive, so they actually sound like perfect Martian species right off the bat. Interestingly, too, one of the lichen species we discovered was actually only the second time it had been reported in North America. So, you know, the more you chip away at, the more you'll discover. And lichens are generally under-collected anyway. And also endolithic cyanobacteria, which is a very scientific way of saying algae, although they're not actually algae, that grow inside of rocks. And so you see the green stuff here in this quartz cobble. Those are actually living cells that have colonized the rock. And these cyanobacteria are actually thought to be some of the earliest forms of life on Earth. They change the rock structure around them, and they create immense amounts of oxygen. So they're not only proposed as one of the future potential life support organisms that we would bring with us to Mars. They could produce a lot of oxygen from our waste products. But they're also thought to be perfect model organisms for how organisms change the rock they live in, and thus what kind of biomarkers would we look for on future missions to Mars for life, both past and present. But after about 2 weeks of staring out at the Utah desert through a tiny porthole, you kind of itch for getting outside and experiencing the wind on your face and all of those things. And of course, a year in the Arctic will be just like that. And so you get the impression that manned spaceflight and certainly these simulated manned space expeditions are really mostly a mental game. And so it will be important to judge carefully the psychology of the crew that goes. And that's just as important as engineering developments and towards the support of manned spaceflight. But I think it's all worth it when you get views like this. And of course, this is Earth, but I don't think views on Mars would be any less spectacular. So I think in the end, anything that we can do to support a mission on Mars will be completely worth it. And if this botanist can contribute in some small way, well, that's pretty cool to me. So at the end of 2 weeks, we were able to finally open the airlock and go outside. And I mentioned that we were all still getting along. So I think this is a feat in itself. We don't really use this picture a lot for talks. We want to be very professional, but and we met up with Crew 144, who is the next round of contestants for this Mars Arctic mission. So that's them there on the right with the beautiful t-shirts where they misspelled Arctic. Sorry. And actually, they were. I think they're stiff competition. The final crew hasn't been announced yet, but these guys included one planetary geologist from Arizona State University, one IT engineer from NASA's Jet Propulsion Laboratory, an MD who works on manned spaceflight, and 2 Mars One hopefuls as well. So I think they'll probably give us a run for their money, but you never know. Also, the guy in the black on the far right, he's apparently Finland's only astronaut. He hasn't been into space, but Finland has selected him as the astronaut to go if they ever do. So I thought that was quite interesting. So once we were through the hab, we were able to, and this is where you get to see my vacation photos. We were able actually to do a little bit of exploring around the deserts. And if you ever get the chance to go, I really recommend visiting the site, not only because of its connection to Mars exploration, but because it's so darn beautiful. I mean, the sunsets throughout the San Rafael Swell are absolutely gorgeous. And you also get the chance to take in some pretty awesome scenery at nearby Canyonlands National Park and Arches National Park in southern Arizona. Certainly very Mars-like, and certainly worth the trip, even if you're not packing your own spacesuit. So thank you very much for your time, and I'm happy to take any questions.
Oh, great.
Thank you very much.
Yeah, we have time for a few questions, and Paul, you can set up the observations for right after this. So, any questions? In the back?
I was noticing that in the earlier photographs you had bacon.
Yes.
Is there some kind of Mars bacon we don't know of?
I wish. No, when we picked up our rations for the 2 weeks, there was actually enough bacon there for every day. So somebody in the Mars Society liked us. And yeah, no, it was American bacon. Yeah.
Go ahead, yeah.
Yeah, I was just wondering what was the temperature that you were working in, the day temperature, and what were you carrying in those backpacks, and how heavy were they?
The backpacks weren't so heavy as they were bulky. So the backpacks were only about 10 pounds each. And they used computer fans for ventilation, so that was what the pipes fed into that connect to the helmet. The daytime temperatures weren't too bad. They were about 15 degrees Celsius. They shut the station down in the heat of summer, though. It would be too hot to do any meaningful work then. The real problem isn't so much the heat in the helmet, it's your breath fogging up the helmet. And that's an ongoing engineering struggle. You're welcome.
I got one up there. Go ahead.
When you were in sim, did you live and sleep by the Martian day-night cycle or the Earth day-night cycle?
We lived in the Earth day-night cycle. Crews have done the Sol, so they've lived the Martian day-night cycle with no ill effects, but just for ease of transitioning in and out of the 2 weeks, we did the Earth calendar. That being said, if we did the year-long mission, I'm sure we would at least try to do a month of living the Martian time.
We'll do one more. There's one right there. Yep. Go ahead.
I noticed that when you're growing the plants indoors, it was only through artificial light. Would they also be using natural sunlight?
They would be. Certainly studies have shown that natural sunlight, the insolation on Mars, would be enough for photosynthesis. It's the greenhouse that they had there was actually really sandblasted, so it was pretty opaque, and the artificial light was there to help offset some of that. Unfortunately, that greenhouse burned down about 2 months after we left the Mars Desert Research Station, so they're currently trying to engineer a better one.
The second part of my question was, when you have Martian dust storms that can block out the sun for months at times sometimes.
Absolutely.
What would plan B?
That would certainly be full spectrum plant grow lights, which we use here, and, for legal and illegal purposes.
I have no idea what you're talking about.
Fair enough.
Okay, we're all slave to the time, so Paul, we appreciate it.
Thank you very much.
You'll stay around for a break, and we can ask questions.
Absolutely.
So, if you have any more questions, grab them there. So we have a bit of a change of schedule. Chris, were you ready for the observations?
No, let's go to break.
Okay. Okay, what do we got here? Yeah, we got... So, in that case, what are we doing here? Let's do the membership benefits for first-time attendees. We have a very good loan library for the telescopes. Our library now, our Stan Mott Library is here in the building. And Estelle, you have is going to be open tonight? Yes, we are. Good. There's our librarian. We're ready to rock and roll there. And Ron St. Martin up there, he's looking after our the FLO down here. Got a lot of work ahead. Ron, you're ready to rock and roll? So what else we got? Okay, and the magazines ourselves, we have a lot of good, very good prices on the astronomy magazines over the years, and I can't remember who was looking after it. Anyway, it's in the website. If anybody wants to know, just ask me and I'll find out for you. We can get very good discounts on all the astronomy magazines that are published. They're not here. Oh, now available electronically too. Cool. So joining, it's on the website. Just have your credit card ready and go from there. The prices are right there. And as I say, you join this outfit and you're in for a great ride. We have excellent talent to help anybody with telescopes. And if anybody wants to know about craters, we can help you out there too. FLO keys, Ron, have anything to say about that?
Yeah, keys available tonight, and I'll be changing the lock tomorrow evening.
Okie dokie. Okie doke. And our break. So, what time is it now? Okay, in exactly 11 minutes and 23 seconds, we'll start her up again. And please get your ticket. Free door prizes here. You don't have to be a member to get a ticket. At this time, I'd like to introduce to you Alan Scott. He's a longtime member here. He was one of our past presidents. Al right now is a scientist at ComDev. He's also was an adjunct professor for 8 years at York University. He has co-authored several papers. Al in the past was president, as I mentioned. The subject of his papers include instrument control electronics. We okay there? Okay. Yeah, this one here is getting a little bit crazy, so don't worry about it. So the subject of his papers, instrument control electronics and space-relevant biological life support systems. So please welcome Dr. Alan Scott.
Okay. I don't know what this is doing. So, thank you for for that, Chuck. I wanted to give a talk tonight to go over the most recent advances in modern cosmology, but I thought to get there we should start at the beginning and go back and really look at why we think what we do about the history of the universe and our place in it. We're very lucky right now that we live in a golden age of science. For the first time ever, I think over the countless millennia that our ancestors stared up at the night sky in awe and wonder and postulated a solid firmament populated by mythical creatures, basic scientific research has now given us an accurate picture of the history of the universe and our place in it. And I want to go over some of the measurements and some of the observations that have led us to this place, and what we know and what we don't know, which is also quite interesting, I think. So let's start at ancient cosmology and the ideas from long ago. We know that the biblical authors pictured the earth as a flat disk floating in water, with the heavens above and the underworld below. The firmament for them was a solid inverted bowl above the earth, colored blue by the cosmic ocean. It kept the waters above from flooding the earth below. A glow within this firmament was responsible for dividing day and night. Lights within the firmament were the stars, and responsible for signs and portents. The ancient Greeks as well had their own system of a firmament. They had a series of crystal spheres, each one associated with one of the moving heavenly bodies. These spheres started with the earth in the center, the imperfect, and moved outwards to the perfect, each layer becoming more heavenly. Each of these heavens, the 7 planetary heavens, the moon, the Mercury, Venus, the sun, Mars, Jupiter, Saturn, they moved independently, and they seemed to move randomly across the sky. They did not always move smoothly. Sometimes the planets appear to go backwards through the sky, as if at the whim of a deity. And that is all that they could tell without the insights of Kepler and Newton to guide them. These nested crystal spheres, at the outside of which there was the heavens. In Latin, this is the empyrean heaven, dwelling of God and the elected ones. Out in the most perfect, where beyond the realm of the fixed stars, which was this sphere here, where nothing moved, everything was perfect and unmoving. Moving on, Renaissance cosmology changed that picture. Copernicus in the mid-1500s moved the Earth from the center out to a supporting role, third from the sun as we know it now. He stuck with spheres because those were the perfect things, and he could not think of any reason why not to use perfect spheres. And again, he maintained that the stars were on a crystal firmament. This model was an improvement on the previous model. It explained the difference as to why some of the planets appeared to move retrograde in their orbits. Because the Earth is no longer at the center, relative velocities make some of them appear to go backwards across the sky. It explained the difference between the inferior and the superior planets, why Mercury and Venus were always close to the sun, and Saturn and Jupiter and Mars were able to go across the sky. That's an interesting symbol. That should be a degree. It predicted the positions to less than 2 degrees, which is roughly as good as the Ptolemaic model. The Ptolemaic model, the Greeks have been adding epicycles over the years to try to account for the imperfections in the spheres and the mismatch between them and the actual observations. So it wasn't really an improvement in terms of the positioning over the other models. There are also some problems with the model. It required the Earth to move. And people obviously realized that the Earth wasn't moving. We weren't flying off of it, and doesn't feel like we're rotating. So there was a problem. There was no model to predict why this could actually be the case. It was an interesting way to predict other things. And also there's been no stellar parallax. Stellar parallax is the way that stars appear to move, nearby stars would appear to move relative to background, more distant stars, as the Earth traverses its orbit, just because of the same sort of thing that you see as you're driving along the road. Close by objects move with respect to faraway objects as we move along. That's never been observed up to this point in the mid-1500s. The stars are maybe infinitely far away. People did not know. Renaissance cosmology continued with the insights of Kepler. His Astronomical nova in 1609 derived universal laws of planetary motion. And this was based on observation. The observations of Tycho Brahe, his mentor, painstaking observations of the position of Mars over 20 years, showed irreconcilable errors with a spherical or a circular orbit. This great data allowed Kepler to move to an elliptical model where the sun was at one focus of the ellipse. The orbits that the planets traced out followed mathematical laws along these ellipses, tracing out equal areas in equal times. But nobody knew why. There was still no physics to explain why this was so. We still needed angels to push the planets along in their orbits. And still no stellar parallax had been observed at this point. The insight was one of Newton's in his Principia in 1687, where he realized and put down on paper the theory of universal gravitation that explained Kepler's laws in a simple equation that showed that the gravity that drops apples to the Earth is the same force that makes the planets move in their orbits. And he derived this universal law of gravitation, and then suddenly we have an explanation for why the planets are moving in these orbits and following these laws. Following this, Edmund Halley in 1718 was measuring the positions of stars, of bright stars. Sirius, Arcturus, and Aldebaran apparently had moved more than half a degree from what Hipparchus had written down more than 1850 years before in his Greek catalogue of the bright stars. And this is starting to lead us to the idea that maybe the stars are actually moving and not fixed. Following this, we go to the modern theory of cosmology. Maxwell, in 1861, came up with the modern theory of light. And Maxwell's equations tell us from magnetism and electricity how light travels as a wave through space with a fixed speed. And this is all well and good, but it is odd that light would have a fixed speed. In the Newtonian world, things move at different speeds depending on the observer. But Maxwell's laws didn't have anything about the observer in them. The speed of light came out as a constant. And so Einstein pushed forward on this with a theory of relativity, the modern theory of gravity. And he basically started with the idea that physics should be the same no matter how fast you move. And so what this means is that no matter how fast you move, the speed of light that you measure is the same. And for this to happen, what it means is that time depends on how fast you're moving. Your experience of time depends on how fast you're moving. Your experience of space depends on how fast you're moving. And different people will see different events happening at different times. One person may see two events that look simultaneous to him, but if someone is moving in a fast direction along the line between those two events, they will see one happen before the other. Einstein's theory of relativity broke down simultaneity. Simultaneous events no longer exist in relativity. You have to specify your speed before you can say anything about past, present, and future. Out of this, he also showed that he united inertial and gravitational mass. Basically, Newton's laws said that masses pull on each other. Einstein said that masses curve the fabric of space and time around them so that objects move in a straight line in space, even though they appear to move in circles. And this is a really weird realization that time and space aren't linear, fixed grids like Newton had thought. The interesting thing was that this could be tested. The predictions of Einstein's theory could be tested. And going through this curvature of space, the curvature of space by the sun, predicts something different than Newtonian physics at the fine level of detail. In fact, there'd always been a problem with the orbit of Mercury. The way it precesses was not explainable in Newtonian physics, but relativity explained it. Relativity also had several other predictions that were subsequently verified. Einstein predicted that gravitational bending of light paths, light made up of massless photons, would not bend in Newtonian physics. But because space itself is bending, the straight line of the photon bends as it passes close to the sun. And this was verified by measuring the positions of stars during a solar eclipse. As they moved close to the sun, their position changed by fractions of an arc second that were exactly predicted by relativity. Further verification has happened over the course of the 20th century. Redshift of light, light moving from out of a gravitational well, the frequency becomes a little bit redder. This was verified around 1960 and onwards in several experiments. Time dilation, the fact that time is experienced differently by different observers, was verified by atomic clocks flying in jetliners in 1972. They predicted gravitational lensing by massive galaxy groups. It was verified by telescope observations in 1979. Predict orbital decay through the emission of gravitational waves. This was verified by the observation of binary pulsars in 1994. Goes on and on. It's an amazing insight, this theory of modern gravity. And this underlies our modern cosmology. And the math behind it we can use to make predictions about the history of the universe. One thing we notice from this is that the shape of the universe is not necessarily what we call Euclidean. We are used to measuring triangles in the local area and adding up the angles to 180 degrees. And one analogy to this is the surface of the Earth. You can see a triangle that you would make on the size of a city. The angles will add up to about 180 degrees. But as you go to larger areas on the curved surface of the Earth, you can see that this triangle adds up to 230 degrees, even though it is a perfect triangle. And the reason is that the underlying geometry of the system in which the triangle is inscribed is curved. It's not a flat Euclidean space. And what Einstein's theory said is that the three-dimensional space that we live in is curved in just this way by nearby masses. So we can build triangles here on Earth and measure them in 3 dimensions, and they are 180 degrees. But if we build larger and larger triangles and there's enough mass nearby, the angles will add up to more than 180 degrees. And this just shows different types of geometries here that one might expect. This is a 2-dimensional representation of a 3-dimensional space. And so Einstein's equations say that there's a critical density. And if the density, the large-scale density of the universe is equal to this critical density, then the geometry of our universe is flat, like a sheet. And no matter how large a triangle is, it will always add up to 180 degrees. But if the density is just a little bit more, then on large scales, we will actually have a closed geometry, a closed universe. The universe will be finite but unbounded. You will be able to move in any one direction, and then you'll come back to your own originating place. And eventually everything in the universe will collapse in on itself. Or if the density is a little bit less than this, then parallel lines you draw will eventually diverge, and the universe will expand away forever and accelerate away, in fact. This critical density we now think is on the order of 5 hydrogen atoms per cubic meter. Seems very low. Most of space is empty, though. And we think from our current observations that the universe is very close to flat. Now, of course, this is on the very largest scales. There's obviously bumps and hollows where planets and black holes and things are, but over the size of galactic superclusters and intergalactic superclusters, if you average all that out, in general, we think the universe is pretty flat. And in fact, even if the universe is flat, it doesn't mean that the universe is infinite. Even in this case here, this is a simple topology. What this means is that there's no connections. You don't wrap around the screen, basically. But Einstein's theory doesn't say anything about how the universe is connected on large scales. It could be that even if the universe is flat, the topology could be that of a torus or something that would allow you to come back as if you were living in a hall of mirrors and you could see the same galaxies over and over again as you look around the universe. We don't really know if that's the case yet. People are looking for that signature in the distribution of galaxies and have not found it yet. So how big is the universe? Well, historically speaking, up to about 500 BC, the world was a small patch of land around your village. Around the time of 500 BC, though, the Greeks realized that shadows change with latitude. And what this means is that we're living on the surface of a spherical Earth. This was known in 500 BC by the Greeks. Around 300 BC, Aristarchus of Samos suggested that maybe the stars are other distant suns. Then, soon after that, there was a problem. The Romans came, there was Dark Ages. Not much happened for a long time in the science. In 1584, Giordano Bruno suggested that the stars might be other distant suns. He was burned at the stake by the church. Although people were still curious, in the mid-1600s, Christian Huygens continued to scratch away at this. He said, what if Sirius was as bright as the sun? We know now that Sirius is actually much brighter than the sun. He said, it must be billions of miles away because of its current apparent brightness. Billions of miles away. In 1838, Friedrich Bessel was the first person to ever measure parallax of a star. This is the 61 Cygni. The parallax he was able to measure was 0.314 arcseconds, a very small change from one side of Earth's orbit to the other. And the distance this signified for one of the nearest stars, 61 trillion miles, mind-boggling. Continuing on with the growing universe, in 1915, Harlow Shapley used Cepheid variables. These are giant stars that oscillate in a fixed period. And we know, and they knew back then, that the period of these stars, by measuring, you can tell by the parallax of nearby ones, the period of the stars depends on their intrinsic intensity. So we have a relationship. If we know the period, we know how intrinsically bright the star is. So we can measure the period and its apparent brightness, and we know how far away it is. So he used these Cepheid variables throughout the Milky Way to measure the Milky Way. And we know now that we're about 30,000 light years from the center of the Milky Way, and the Milky Way is, twice that big at least. Following this, there was a controversy, the famous Shapley-Curtis debate in 1920. At that point, the Milky Way was thought to be the entire universe, just our galaxy. But there were these intriguing little spiral nebulae that people keep seeing, and they seem to have a really significant number of novae in them, more than you would expect in a small nebula. And people started to think, maybe these are other universes, other island universes. Several people, though, were a little bit worried about that. It pushed people beyond their comfort level to realize how drastically far away and isolated these things might be. They actually were able to use in 1924 Cepheid variables in the Andromeda Nebulae to answer the question, and finally, that these spiral nebulae were other island universes. The nearest one to us, the nearest major one, the Andromeda Galaxy, is 2.5 million light years away. This was how the universe grew. Following on, we now know, because of the finite speed of light, that distance equals age. The further back we look with our telescopes, the further back in time we are looking. So we actually can look at, in our nearby area, normal-looking galaxies that look similar to the Milky Way. And as we look back further, we've taken a couple ultra-deep pictures with the Hubble Space Telescope, looking at what we think is the evolution of galaxies over time, from simpler to more complex. Einstein's model, of course, tells us that the universe is likely to evolve. If it did not, it would probably collapse back in on itself in a big black hole. So looking back in time, we can learn something about the history of our universe. And in fact, there is evidence that emerged in the early 20th century for something that we call the Big Bang. A couple of people, Vesto Slipher first in 1912 and Edwin Hubble later in the 1920s, took spectra of nearby and distant galaxies, and they found that there seemed to be a scaling in what's called redshift. So here we see spectra of a star in our galaxy, a nearby galaxy, and two what look like smaller galaxies angularly on the sky. And if you spread out the light, you have this fingerprint pattern of mainly hydrogen absorption lines. Hydrogen gas is absorbing the light from the background stars. And that pattern shifts to the red. And what we found was that for the distant and even more distant galaxies, they were always shifted to the red, and more red the further away they appeared. And this was what they called the Hubble law. It looks like, and we know from the theories of light, that light shifts. The wavelength of light shifts as an object moves away from us, like the Doppler signal in, say, a train's whistle shifts as the train's coming towards you. It's high in frequency. If it's going away from you, it goes lower in frequency. Light does the same thing. What this could indicate is that faraway galaxies are moving away from us very quickly. And so it appears the farther away a galaxy is, the faster it's moving away from us, shifting its light to the red. Well, what does this mean? Did we make some sort of cosmic mistake and all the galaxies are running away from us? Well, no. We can actually come up with an idea that explains this. In 1927, in fact, the Belgian priest Georges Lemaitre was the first to propose that the universe began with the explosion of a primeval atom where all matter and energy was contained. His idea was that this atom explodes into a pre-existing infinite space. We now know that that's not quite correct. What we now know is that all the matter and energy in the universe was crammed into a dense place, including the space. And what happened was that the space itself expanded. Every portion of space expanded from a primordial fireball and then began cooling over time. An analogy is a raisin bread. The raisins are galaxies, the bread is the space between. As you bake the bread, the raisins move farther apart, and the further the raisin is to start, the faster it moves away from you. This same picture is seen by every raisin in the bread. So we aren't in the center of the Big Bang necessarily. What we're in is an expanding raisin bread of galaxies, and space itself is expanding. Another more intuitive, something that may be more intuitive for some people, is to think that none of the galaxies are moving and everybody here is just shrinking. And in fact, it's completely analogous, because all we can do is measure the ratio between our rulers and the spaces between galaxies. And we know that either we're shrinking or they're moving away fast. So how old is the universe? Well, we can measure the Hubble flow, or the speed, redshift of a galaxy with distance in various different models. You can look at standard candles like supernovae, which we know the intrinsic brightness is roughly the same, and we can measure the redshift versus the brightness of these things, and we plot this curve. This is the Hubble curve. The Hubble Space Telescope key project. Hubble Space Telescope was designed to measure this expansion history of the universe, and we know now that the Hubble constant is 67.8 kilometers per second per megaparsec, and if we integrate that back to the point where everything was in the same place, it's 13.7 billion years. So this is the first time in the history of our race that we actually know how old the universe is and what our place in it is. Several independent methods give roughly consistent numbers with less precision than the models that we use. This brings up a problem, though. We call it the flatness oldness problem. It's not really a problem, it's really a good thing. For some reason, the universe seems to be perfectly balanced on a knife edge to be flat. We know that if it had a little bit more density, even 1 nanosecond after the Big Bang, in fact, to the 25th decimal point, the density is very important. If it was 2 points in 25 figures less or more, it would have recollapsed by now in another big crunch. If it was a few points less, it would be accelerating apart just due to the gravity right now. So this is what we call an interesting coincidence that we don't really have a good explanation for. And it's one of those things, some people could think it's an anthropic principle. Maybe these other universes aren't amenable to life. Human life wouldn't be there to observe them, so therefore, because it's kind of a circular argument, other people postulate a special god of the gaps who likes to balance mass energy. Or there could be some new physics. One of the really interesting things, though, that came out of Big Bang theory is Big Bang cosmic nucleosynthesis. If we run everything backward, this was first posited by a famous paper by Alpha, Betha, and Gamma, which, Alpha, Beta, Gamma, it's very funny. Betha wasn't actually involved, but they brought him in just because of the title. In 1948, we knew a lot about nuclear physics. We knew the cross sections and the rates of reaction at temperature, and we could actually predict, based on thermodynamics and nuclear physics, what might have happened in those first few minutes as the Big Bang expanded out. And we've run the models, we know the cross sections. What should happen is that we should have 75% protons, 25% helium-4, traces of deuterium, lithium, and beryllium in the primordial universe. And in fact, everywhere we look, the ratio of hydrogen in the universe to helium is 3-to-1, just like nuclear physics predicts. This is one of the key stones of evidence on the Big Bang, that our understanding of nuclear physics in the first few minutes, up to 20 minutes after the Big Bang, predicts the ratio of hydrogen to helium in the universe today. And the density of deuterium and other traces tells us a little bit about the amount of matter, the density of matter that was in the universe in these early times. So this is really an amazing prediction. And from this we know that from the deuterium concentration of the current universe, it's a little bit low actually. We know that the density of matter that would be needed to produce the deuterium that's in the universe, and it's actually only 20% of what we would need to make a flat universe. By Einstein's equations, the universe should be expanding rapidly away. And this is when the postulation of dark matter came in. This is one evidence for dark matter, and there are other evidence that support the existence of dark matter. But dark matter is a non-nuclear matter, some sort of exotic thing that provides gravity and density, but does not actually participate in these reactions. So that's an interesting side effect. After nucleosynthesis, we have everywhere in the universe a hot primordial plasma, populated mainly by high-energy photons, like what we find inside the core of a star. And as the universe continues to expand, it continues to cool. The temperature drops. It's like moving from the core of a star out towards the surface, but we're not moving in space, we're moving in time. As the universe cools down to 10,000 Kelvin, the protons start to recombine with electrons. However, we have to wait until it cools to about 3,000 Kelvin before neutral hydrogen can form and not be immediately reionized by the photon soup. At that point, photons decouple from matter and are free to pass through the universe. We change from this foggy plasma to a transparent universe at this temperature. So, if we could postulate an observer in the early universe, you would find yourself in a red fog that slowly dissipates over about 100,000 years. The sky in all directions would be red hot, as though you're in the center of a blast oven, and would appear to cool slowly to black over millions of years. As the universe expands and the wavelength of the cosmic background echo of the Big Bang shifts out of the visible spectrum. In fact, Alpha, Beta, and Gamma predicted that we would still be able to see the afterglow of this explosion if we looked far enough away. It would be shifted into the microwave, and it would appear like a black body between around 5 to 50 Kelvin is what they thought. In 1964, a couple guys in Bell Labs made the most sensitive radio dish ever built. There shouldn't have been noise, but wherever they pointed it, they found a microwave hiss. they had actually discovered this afterglow. They got a Nobel Prize for this discovery. This microwave background is coming from all directions. It's 3 degrees Kelvin. It's the temperature of the universe from this fading blast furnace. It's actually almost a perfect black body, as you can see. We can tell very precisely what the temperature is. If our theories are correct, we are looking back in time 13.7 billion years to the afterglow of the primordial fireball, a universe-spanning star that was aged about 380,000 years when it last emitted this light. Of course, a perfect featureless background would not be consistent with our understanding of cosmic history. For galaxies and clusters to form, there must have been some hot spots and some cool spots. These would serve as condensation cores for gravity to begin accumulating matter into galaxies and galaxy groups. These would be also formed as sound waves in the plasma, ringing from the Big Bang itself. To see these, we would have to send up a satellite, so we did. The Cosmic Background Explorer was launched in 1992, and its job was to find the echoes of the Big Bang and map them. And this is an all-sky map in a color scale of about 0 to 4 degrees. And you can see that it's a very featureless 2.728 Kelvin. But if we subtract the mean black body off of this, this is what we see. There's a distortion, and it's about 3.3 millikelvin, and it's a dipole. And this is expected. This represents our motion with respect to that last scattering surface. This is a Doppler shift. We are moving towards this area of the sky of the average velocity of the universe back then, and away from that area of the sky. And so if we subtract this dipole off, this is what we see. We see thermal radiation from the Milky Way galaxy in a big red band. And if we subtract off the thermal radiation from the Milky Way, this is what we are left with. If we are right, this is a map of a spherical shell through the universe as it would have appeared 13.3 billion years ago. At the time the light was emitted, this map would have encompassed a sphere of 42 million light years in radius. At the present time, I use scare quotes around present because of relativity, the fluctuations we are seeing in this map would represent galaxy clusters that have now expanded away from us and are now 46 billion light years away from us. This is as far back as we can see with telescopes. We sent up other satellites to learn more about this background radiation. In 2008, we launched the Wilkinson Microwave Anisotropy Probe to look at this with higher resolution, to map the size of the oscillations that eventually form galaxies. Astronomers are looking for patterns in the background radiation that might tell us about cosmic geometry. If we correlate the angular size of the ripples with the size of the galaxy clusters and superclusters, based on our models of cosmic expansion histories, we can find remarkable agreement. And in fact, 2014, the WMAP team released its analysis of the microwave background data that shows that the observable universe at the scale of this map is flat within 0.4%. So we're very Euclidean over largest scales. This was followed by the Planck satellite in 2013. Planck was set up to measure polarization in this background. And in fact, one of our I think our news item last month discussed the polarization of the background. Planck is refining the map, and it's hoping to find fingerprints from cosmic inflation on these ripples. And the ripples, in fact, can be correlated with angular scale. And there's what you get on the right is a power spectrum of different angular scales and the ripples of this background radiation. The statistical distribution of the size and density of the hotspots tells us something about how sound waves traveled through the plasma in the early universe. It tells us about the density and the viscosity of the universe at that time. And it strongly constrains the set of initial parameters that resulted in our universe today. Cosmic inflation is consistent with the pattern shown here. In fact, the red line is our model, the dots are the observations. Many more exotic theories have been ruled out by this. So just to get to a point where I can recap a little bit about our understanding of galactic evolution and what we know from looking back in time with our telescopes. This is the Hubble Ultra Deep Field. And more distant galaxies are redshifted, looking orange, and then the most distant ones are just single pixel red spots. This type of image suggests that there are more irregular dwarf galaxies at deeper redshifts. And this suggests that older galaxies were smaller. I mean younger galaxies. Galaxies that are further away in time from us were smaller and in the process of coalescing into larger modern galaxies. There also appears to be orders of magnitude more star formation going on in these older galaxies than there is in the current universe. We've found quasars in the far distant universe, very highly redshifted, extremely bright objects, which we think are gigantic black holes at the cores of early galaxies, accreting mass and beaming radiation out into the universe. These are mostly seen in the distant universe where there's still a lot of gas coalescing into stars. The spectra of these quasars, though, show superimposed absorption lines from light passing through interstellar clouds of neutral hydrogen, also at high redshift. We now expect that a few 100 million years after the electrons and protons combined to neutral hydrogen, that the first stars were formed, and these stars started spewing out ultraviolet radiation and reionized these neutral clouds so that they no longer were able to absorb the quasar light. And that's consistent with what we see in what we call the Lyman alpha forest in these spectrums. Globular clusters, even in our galaxy, appear to be undisrupted remnants of an earlier time. They consist mostly of old red stars, these globular clusters. In fact, the oldest known clusters have metal-poor stars, suggesting that the universe has become enriched in the heavier elements from supernovae over the years since they formed the first stars. Theories of stellar evolution, based on our knowledge of nuclear physics, show that most of the ages of the clusters are younger than what we think the universe is. There are no anomalous clusters out there that are clearly older than our estimated age of the universe. So what's this dark matter stuff that I mentioned before? This came about mainly in the 1970s. We know that the geometry of the universe is close to flat, but the density of normal matter, the matter that we understand, is nowhere near what is needed to make it flat. So other things that predict the existence of dark matter, that galaxies actually rotate faster than they're expected to rotate. We can measure the rotation rate of galaxies by looking at the differential Doppler shift in an emission line across them, like this map here. The red is moving towards us, the blue is moving away from us. We can measure the rate of galaxy rotation by taking these spectra. And we would expect, based on the light from the stars, that, and Newton's theory of gravity, that the rotation rate should slow down as you get towards the outside. But they don't slow down. They rotate as though they are solid bodies. And what this means is that if our theory of gravity is correct, there should be a lot more mass extending a lot further out of the galaxy than what we see in just the normal matter. And this is what we call dark matter. Another recent surprise is dark energy. Nobody was expecting this. Astronomers were measuring standard candles. They were taking censuses of distant supernovae, and they wanted to measure their brightness versus their distance, and they expected that the universal expansion from the Big Bang would be slowing down due to gravity. We expect in a flat universe that things should slow down and then eventually peter out in its expansion. What we found actually was the reverse. Typical magnitudes of these supernovae are about minus 19.3, in absolute magnitude with little variation. We were able to find this expansion, and nobody knew what it was. Nobody knew why it was there. And so they postulated, they gave it a name, and that made them more comfortable. Dark energy. So, based on our best models, we now believe that matter is 30% of the mass energy content of the current universe, and dark energy is 70% of the current density. And this dark energy seems to be accelerating the cosmic expansion rather than decelerating it. So that was a surprise, and it led to a Nobel Prize as well. Now I'm just going to touch on inflation. This is also something that came out of the 1970s, and it was introduced to try to solve a few problems in our understanding. One is that coincidence of the flatness oldness that I told you about before. Inflation is when they had the Big Bang and suddenly the universe went through some sort of a quantum field transition and everything expanded much faster than the speed of light. And what happened, what this also explains, is why the universe looks the same temperature in both directions. We don't understand why the universe is the same temperature in all directions. A priori, you could just say that it's that way, but that's not a good explanation. So why is it the same in both directions? Well, they said that they were initially in contact and they were stretched out by inflation. That's the layman's version of it. But what we think we know now is that inflation is running into problems. Inflation actually has to be very fine-tuned to produce the sort of universe that we find as well. So it doesn't really solve the problems, it just pushes them back a level. It gets rid of the monopole problem. Many of our theories suggest that the universe should be filled with extremely heavy magnetic monopoles, and they're not there. So inflation suggests that they were initially there, but then they were inflated away. So why aren't hypothetical particles seen? Because of inflation. It also predicts a unique pattern of polarization in the background radiation, and this is what the Planck mission is looking for. And there was a preliminary announcement that it had been found last year that was promptly retracted because the data was wrong. But they're continuing to analyze the data and refine it. It's not going to be a bright signal, they don't think, but they may find it. We have to reserve judgment until the data comes in, but interesting times ahead. So I'm getting to the summary part. What do our current models tell us about the current universe? The age of our current universe is 13.7 billion years old. The size of the universe is 93 billion light years. That seems to be a contradiction because we know that the speed of light is such and such. How could the universe be larger than a radius of 13.7 billion light years? Well, that 13.7 billion light years that we're looking back on to see the Big Bang radiation has been stretched over that time period, just the same way the light has been redshifted. So, as I said, those points on the map of the background radiation are now 46 billion light years away from us in what we call a co-moving frame. If we were sitting there and they are expanding away in the same Hubble flow that we are from the Big Bang, it's much larger. Because it's the metric defining distance that is changing rather than objects moving in space, this expansion that we see is not restricted by the speed of light, of course. The expansion of space, the stretching of space, can exceed the speed of light if it wants to. There's nothing in Einstein's theory that constrains the stretching rate of space. Einstein's theory deals with the movement of objects through space, physical objects moving through space. If the metric that defines the distance between objects is expanding, it can expand any way it wants. So that's an interesting way to think of it. But basically what we know now is that the universe is 4.6% atoms, 23% something we don't know, and 72% something we don't know. But I always say that the road to knowledge is admitting what you don't know. So now we know what we don't know. And it's an interesting time because now we can find out what these things are. And people are are planning the next generation of spacecraft that are going to map the three-dimensional structure of galaxies to even better precision in the distant universe, so we can learn more about what this dark energy is and what the real expansion history of the universe has been. What's the fate of the universe? Well, we don't really know, because we don't know what dark energy is going to do. Naively, we would think that we're kind of a flat universe, and so what's going to happen is the big freeze. Without dark matter or dark energy, things would just expand forever, cool down, and freeze. The universe continues to expand asymptotically forever. After 100 trillion years, all the stars burn down to cooling white dwarfs, neutron stars, and black holes. After 10 to the 37 years, all that is left are a smattering of black holes slowly evaporating through Hawking radiation. The universe then becomes a uniformly warm soup after a few trillion years with no free energy. After a Google of years, only the waste products from these processes remain, mostly photons of colossal wavelength, neutrinos, electrons, and positrons. For all intents and purposes, the universe would have dissipated. The Big Rip, of course, accelerates this process immensely. If dark energy continues to dominate the universe, and we don't know what it's going to do, it might, it could strengthen until it overcomes all of the binding forces that hold us together, rip all the particles in the universe out to unimaginable distances, and leave behind a void. The Big Crunch is the opposite, of course. The acceleration of the universe could end by gravity. Everything ends up coming together for a cozy homecoming. There are also corollaries of this theory called the Big Bounce, where it comes together and bounces out again and starts the whole process once again. Of course, as I say, there's a lot to learn yet. There have been some interesting controversial observations, and I'll just touch on them briefly before I finish here. Other people suggest an ending in a vacuum transition brought about by one of these super colliders, which create another inflationary period or trigger it. Most physicists think that's pretty unlikely. Not enough to stop doing it. So, summarizing the modern advances, for the first time in history, we have a cosmology based on observations rather than myth. We've mapped the three-dimensional structure of the local universe. We know the age of the universe to better than a few percent, and most things that we measure are in agreement with this. We appreciate for the first time the awesome vastness of the universe, billions of galaxies, each with billions of stars. And we've learned that there's still a lot we don't understand. And just as a teaser, I'm going to show you some of the tantalizing stuff from the new maps. The data that we have now of the cosmic background suggests there may be a north-south asymmetry. There seems to be, this has been highlighted a little bit here. This isn't, and there's a cold spot over here. This could mean that we are seeing some weird topology, wraparound effects perhaps in the universe. Or it could be something that tells us about how the constants, the physical constants of the universe may be varying over cosmological distances. We don't know. This is just speculation at this point, but it's interesting to think about. In fact, I've mentioned in the past about some other controversial observations. People have looked at quasars and they've found there's an asymmetry in the physical constants that govern the absorption lines in quasars, and it just happens to be 1 part in 10 to the 5th between the north and the south hemisphere. So perhaps there's something there, perhaps not. Interesting to follow along and see what comes out of the new measurements that we're making. Thank you.
Thanks very much, Al. Yeah, we're stuck for time, and relatively we're out of time. So any questions, Al, will be free after the meeting. And we'll start with the observations now. There we go. First one, Gary. Where are you? Here we go.
Evening, everyone. If we can have the first slide, please. Well, back in February when you guys were freezing here in Ottawa at -40, my wife and I were lucky enough to take a Caribbean cruise. And this is a shot from the, oh, I did it again. Which one is the,
This one here. I'll you just
Okay.
tell me why.
yeah,
There we go.
yeah. But the slide before was, if you can just bring it back for a sec, you'll see Sirius and Canopus. Canopus is right on the horizon, just past the wing. Never seen Canopus, only when you're landing in Florida. You got to be in the southern part of the continent. Okay, next slide. This was the Norwegian epic. The first day we were in Jamaica, 7 a.m., 27 degrees. And I think you're about -40 that day. So I had a great cruise. I was very fortunate to actually give my astronomy talk on board entitled Our Cosmic Origin, which I've been doing a lot very recently. And asked Norwegian, and they said, yeah, go for it. And I had about 70 people that enjoy the talk. So now I've actually gone international on the outreach. Well, just if you can, do you have the pointer?
Yeah, the pointer is right there.
Oh, great, thanks. Yeah, so Comet Lovejoy is still alive and well. It's around 7th magnitude, and here's Cassiopeia the Queen, obviously. So it's moving on out into Cephas right now. So it's still there, and it's the brightest of the pretty well 12 comets that we can see nowadays. Next slide.
Oops. There we go.
There we go. One of the auroras that we had last couple of months ago, or last month, not a great shot. This is an artifact of leaving your ultraviolet filter in front of your lens. So just want to warn you, when you get the aurora of the century, take that filter off. So it wasn't a great shot. Here we have the nova. It's still in Sagittarius. It's still pretty well naked eye, dwindling a little bit. This is rising about 3 o'clock in the morning. And that's it for observations. Thanks, folks.
Thanks, Gary. And James?
Yeah.
Rock and roll.
Okay. So last month, I spoke to you about my wife and I. We took a trip to Alaska to see the Northern Lights, and I showed you some photos. Well, I actually have some more photos to show you, and this is from the tour Dropbox. So these are really excellent, high-resolution photos. So we'll just run them by. There we go.
Awesome.
Be a little slower.
Yep.
A little slower. As you can see the stars there.
You can see the colors.
Yeah, yeah. Quite a difference. That's an interesting color as well. Yeah.
Awesome.
Oh, that's a nice one. Okay.
Thank
So
you very much.
hope you enjoy.
That's me. That's my.
Want to drive?
No, you can drive.
Okay, tell me when.
That's my selfie picture from Nirvana. Well, that turned out to be an exceptional night. The next picture there, that's how the night started. We showed up just before sundown, started setting up our gear, and we could tell that there was going to be an aurora that night. So I decided, well, I'll set the camera up and just let it run while I finish setting up. Well, lo and behold, it kicks up like this, and then a meteor goes right through the frame. I couldn't have asked for better. Perfect. And then within 30, 40 minutes from that time on, they died down. Oops. And it was a beautiful night seeing for the rest of the night. This next picture is my favorite. I took this on the 14th of this month, or well, just last month, April. I work from home, so whenever I get a chance, I try to set the solar scope up and see what's going on. Well, this day, I set up, and I could see this CME streamer coming at the eastern limb, and it was quite amazing. So by the time I had run back in the house, grabbed the camera, and set up to take the picture, it was already diminishing. And in the time I was taking the picture, it was diminishing. It only lasted about 20 or 30 minutes. But if you take a look at the disk of the sun, that's about, well, the measurement is roughly 1.38 million kilometers across. And that CME is probably about 500,000 kilometers. To give you a reference, take a look at any one of those sunspots on the top right, and that's roughly the size of Earth. So that's one massive CME. Now, with this picture, I have to express, this is a single shot. I don't stack, I don't do multiple pictures, I don't do any exotic processing here. What I tried to do was process it as well as I could without having to take multiple images of just the prominences and then the disk. So this is one picture. Had I done extra processing, I could have brightened up the CME, but I tried to preserve it as best as possible the way you were actually seeing it. And my style is more photojournalistic style, so I prefer to minimize any processing that I do to the images. So that was on the 14th.
Thank you very much.
No, thank you.
See, here we go, Paul. I got a question about that blank in the middle. I'm sure you do.
Hi, everybody. Sorry, I wasn't here last month to show you some of the auroras from St. Patrick's Day, so I pushed them into this month. But yes, unlike others, I was stuck here in Lanark. Too bad. And managed to see the aurora that we had on St. Patrick's Day evening. We got a pretty good view on the 17th. Had a follow-on display on the 18th. Temperatures were about probably as cold as they were in Alaska. You maybe wasn't as good, but it was still fairly pleasing. I just want to throw this in to show you why we had that. Where's the pointer there? Thank you. Why we had that.
The pointer is this guy here.
Oh, is it? Okay, thank you. Why we had that rather significant display. You can see this is the auroral oval. This is a projection that's done I think it's on an hourly basis. And when I saw this that night, because I monitor this fairly frequently, I could see that the projected visibility line, there's us right there. So it's unusual to see it like this. This indicated a pretty hot occurrence of the aurora there. And I thought, yeah, that might be something that we might see. And we were fortunate enough to have a clear night. So I set up two cameras, set up one at my place in my backyard, where I do have some trees to the north. And as such, don't have visibility right down to the ground. So I just set up one camera there and let that roll. And then I went down the road there where I had a much more open sky and managed to get a couple of nice shots of the aurora. So the first one there, please.
Okay.
You can show it? Oh. So that's just a shot from my backyard there. And as you can see, there was the tree line was blocking most of the interesting part, because from where the camera was sitting, that tree line's probably about 25 degrees elevation. But you can see the red tops, the reddish parts of the aurora tend to occur in the higher part of the atmosphere, and so those were protruding above. This was done with just camera stationary on a tripod with a Bauer 8mm telephoto lens, and that's why you've got the curve going on there. So down the street was a much more interesting situation because much more open. And that was the view that I was getting down there. So that was with another camera, just stationary on a tripod, and with a Bauer 16mm lens. So it's about an 80-degree field of view across there. And as you can see, it was fairly nice actually. We got down when you could see the lower elevations. You could see the green transitioning up to the magentas and up to the deep blues up above there. So it was quite active. So what I did with this is, oh yes, yeah, no, that's fine. You can show that one. I had a couple of different cameras going there. For a time, I also canted the camera to the west because I noticed this rather interesting thing. You can see this is Orion setting down, just getting ready to set down in the west, and there was this band of red auroras quite removed from the north. Like in the north, we would have been looking at the auroras up here. This was almost due west, and you could see there was this bright auroral band kicking up through there. And I thought that was rather interesting because it was quite separated from the main show going on in the northern sky. Next one. The following night, Eric LeMay came out as well, and we were waiting for the big burst there. It wasn't as bright as it was the previous night, but we did at one point notice a very odd cloud forming again in the western sky. You can see that that's the Rosette Nebula, just getting ready to set down below trees. So very close to the ground. It's only a couple of degrees above the horizon there, but this cloud was really interesting. It pulsed in probably about half a dozen times. It got really bright, very noticeable, then it would fade down, and it would come back up and fade down. So I just threw the camera over there and grabbed this interesting picture. There was no structure really to the aurora, but it was just pure red like that. So yeah, it was an interesting night. So what I did with these images, I wasn't just shooting single images. I set the camera up to shoot consecutive images, just one after the other. So it's a hands-off operation, and I can just look around and enjoy the sky there. And the benefit of doing that is that it also allows you to stitch it into a movie to make a time lapse. So if you can, is that our next one there? Yeah. So this movie I'm about to show you, you'll notice a change in the scenery. The first part is from the camera that I had set up in my backyard, and then the second part, the more open part, is from the camera that I had set up down the road there. So this is a combination, especially the second part, the longer part, of about 300 odd pictures. Taken over about a 2 hour, 11-minute time span. So 15-second shots with a 15-second break in between, and just carry on like that. So if you can roll that, you can see how the aurora danced for us that night. So this is the view from my backyard.
Cool.
And it really strobed at points there. But you can see the rotation of that coronal auroral oval. And then it would subside for a while, and then it would flare up again. It's quite dynamic, actually. You can see obviously the rotation of the stars. Yeah. So again, that second part is compressed. It plays, the second part of that, where we shift to the other scene, is about 30 seconds long, but the actual duration there was some 2 hours and 11 minutes. As you can tell, the sky is rotating quite quickly there. But I was amazed at the structure and how intact the structure stayed, and the rays as well, as they would move from right to left in the course of that time. So it was a good night for us there. St. Patrick's Day, a lot of green. That was seemed very appropriate sometime. So yeah, not quite perhaps as dramatic as what was in up in Alaska there. So the last one I have for you here. This is an image that stems from Norse mythology, and Thor is the god of thunder, and he's most known for his weapon, the hammer, and a winged helmet there. And 15,000 light years from here, there's a nebula that bears an odd resemblance to that helmet. It's Thor's helmet. Cool. And so I shot that in February. This is a composite of about 8 hours of exposure taken through narrowband filters over 4 separate nights. It uses a modified Hubble palette to put it together because these are narrowband exposures there. But it's a fascinating nebula because it's about 10 times farther away than the Orion Nebula, about 30 light years in diameter. And that star at the center, it's a Wolf-Rayet star. That's what's causing this nebula. The star was moving through a much larger molecular cloud, several hundred, if not more, solar masses of material moving around there. But because of its activity, it's energizing things, it's stirring things up, and with the winds coming from the Wolf-Rayet star, forming this beautiful elaborate structure of Thor's helmet there. And that star, it's a good thing it is as far away from us as it is, as I said, about 15,000 light years. That star is will probably blow itself to pieces in the next 1 or 2 years. This is believed to be in a very pre-supernova stage there, so it could pop off anytime. And in fact, it could have even popped off sometime in the last 15,000 years, and we wouldn't know about it. But yeah, when it does go, it'll probably mess up that very pretty looking nebula. So for those of you with big scopes and dark skies, check it out while we can. All right, last one I have for you. I am running my astrophotography course at SPOW. First installment is tomorrow, then the following Saturday as well. I would have announced this last month, but again, sorry I wasn't here. I did mention it in March there. So if you're at all interested and you have to have the time to take it in, you can still come tomorrow morning. We start at 9 o'clock, so rise and shine, right? So just to let you know that that's available. Okay, Chris wanted me to mention, yes, for International Astronomy Day, the museum here was kind enough to let us set up our equipment and bring our bodies there, complete with chairs, and help people out with telescope issues there. So we advertised this in various media there, including through Focus Scientific. They obviously have a lot of newbies getting telescopes at Christmas time. People need a hand with these things, so we made ourselves available. A number of our members made ourselves available there to help people figure out which end of the scope to look through. Yeah, that sounds funny, but trust me. Yeah, so it was a good session there. We had quite a number of people through. We had people coming and visiting our RSC display inside the museum, and we had quite a few people come out and actually bring their stuff. We'd help them set them up. We'd show them how to do their alignments, and so everybody went away happy. And I think we have some budding observers, which was good timing, especially now that the weather is getting a little warmer for us. So thanks again to all the folks that did come out and offer their time to help out in that endeavor. Thank you very much. Thank you.
I'll just let it slide through here. This is pretty cool. Yeah, we had a good time. Oh yeah, I can see. We had a real good time. Actually, the best thing I had was good questions from kids. I'll tell you the advanced questions you get from these guys. Jim? Here you are.
Sorry to come in so late. I think the club is divided into 3 groups. I'm the director of SmartScope, and the first group are going to say, well, I hope Jim's got something positive to say about SmartScope tonight. Second group's going to say, I wonder what's wrong now. And the third group's going to say, what's SmartScope? Okay, it's late, and I won't take long. Sorry to disappoint the first group.
Jim, come closer to the mics.
Okay, how's this?
That's better.
Okay, I'm sorry to disappoint the first group. We've had a problem. So the second group, you're the big winners tonight. I'm coming at this time because on Tuesday night, we were in the final stages of collimating the scopes when the dome drives broke. The dome drives are the electric drives that turn the dome in concert with the telescope. It's not the first time they've broken, and this time it sounds like they're irreplaceable. I can't get the electric motors for them, and the only options, well, is to buy a new part. However, what I'm asking for tonight, for information from any member who has a usable, tested dome drive that they hand built, so we might be able to copy it and use it on SmartScope. Because as it stands now, these factory ones, this is the first problem. The little pins that hook up to the belt that drive the dome, they broke off twice. 3 times, I think, Wolfie. And then we finally got that fixed last year, and this year the motors started to smoke, and the manufacturer won't sell us any motors. So consequently, my question again is, are there any members here who have a homemade dome drive that'll drive, say, a 10-foot dome that we can look at and copy. I'm available at jim.maxwell.5@gmail.com. And this is that's the motor aspect part of it. And that's in pieces over here if you're interested in seeing it after the meeting, or if you'd rather go home. And finally, what's SmartScope? It's a project we started 15 years ago. It cost us $100,000 as a club. And the idea was to build a remote operating telescope that we could hook up to a computer and give presentations from the computer itself. For a number of reasons, the project fell into disuse. For the last 5 years, we've been trying to fix it. It's like de-mothballing something, because every time the more we use it, the more stuff we break. And because of this winter past, where we had no time at all because of the cold weather and the cloudy skies, we're trying to get up and running again. But frankly, moving those domes by hand is not fun. And so if we can find a good homemade electric alternative that we can use and hopefully get parts for easily, we'd be much appreciative. Anyway, thank you very much.
So some announcements. The tour for April 11th. Do you have anything to say, Ron? Where'd you go? Okay. This looks like good turnout out there. And the public observation at the Carp Library, our star parties. These are all announced on the website, and the go, no-go decision will be made that day and be announced on the website itself. So the next one is May the 8th coming up, and of course the rain date's coming after that. Public outreach, where are we here? There we go.
No, I don't need to click anything, thank you.
No.
I've been asked by the Royal Canadian Air Cadets to do a stargazing night at the location in Spencerville, where they're going to be training for the weekend. And well, I need volunteers that could bring a scope and help me with about 70 really enthusiastic kids.
Rock and roll.
Voila! It's on Saturday, May the 17th, which coincides with another event, which will be the next slide. To my sadness, we don't have any wine, but we have lots of kids.
Yeah, lots of fun.
Probably, thanks. Oh, and I'll be sleeping in the chair over there at the end of the meeting, so you can just come and see me if you want to come and spend the evening with us. Thanks.
And the next announcement? Where are we? There we go.
Hi everyone, my name is Prajesh. You guys may recognize me as the Star Party coordinator from last year. And this year I've been able to reach Blue Gypsy Wines as an alternative for Star Parties. However, they seem to have their own events going on during the summers as well. So at Blue Gypsy Wines, they open up their facility for stargazing, and they'd also like some volunteers to come from RASC. That's something I've organized. There is a $10 entrance fee. However, you also get to go in for tastings. So the winery will be open for tastings at the same time as you guys do your stargazing, and they have requested for some volunteers as well, who will be exempted from this fee if you guys show up. So unfortunately, it's on the same night as that of Sylvie's event there. And yeah, well, if you guys would like to volunteer, you have to sign up beforehand. And I do have my iPad here in case you guys want to just drop your name and email. So you can just talk to me after, or just email me at joshyprajesh@gmail.com. So yeah, thank you very much.
Thank you. Wine and astronomy, what could possibly go wrong? The library is open. Estelle, it's just down the hall, is it?
It's right behind the screen.
Okay, shows you what I know. So as soon as the lights come on, the library and Estelle will be open for business. Information, Ron St. Martin, we had him earlier. Estelle is right here for the library. The Lone Library, Alan Scott, Dr. Scott gave us the presentation. Coffee and conversation out in the hallway for compliments of Van and Art Fraser, beautiful. Membership information, Art Fraser. Sky Telescope Astronomy renewals. It's, where are we here? Stuart Glenn is looking after it. Where are you, Stuart? Anyway, on the website it's there, and just let us know snacks, drinks, and etc. at Perkins as soon as we finish here. So again, thank you very much for showing up. It was a great evening. I loved it. And we will be on the website very, very shortly. Where are we here? Okay. Here's the website. All the videos from our presentations are posted there. Review them anytime you want. 101 tonight, great. Loved it. Thank you very much, and we'll see you next Friday, or not next Friday, but June the 5th. Oh yeah, the door prizes will come up. Don't you worry. 5th of June 2015, and we have a swap table then. So again, drive carefully, have a good time, enjoy the stars, and we'll see you next month.